In this part 2 of sketching quadratic functions, we're going to look at sketching graphs that are in this form, the general form of a quadratic equation where we have ax squared plus bx plus c. It's not easy to see what the transformations of that function are, so what we're going to do is switch the equation to the standard form, and we're going to do that following these steps, which include something called completing the square, which will remind us of our work with trinomials and factoring that we did first semester. So here's an example. F at x equals 2x squared minus 12x plus 7. The first step we're going to do is factor out that a value, that 2, and we're going to factor it out only from the first two terms. So we'll have 2 times x squared minus 6x plus 7. At each step, you should be able to reverse what you've just done and get back to the original equation, okay? Now let's take a look at that binomial that's in the parentheses there. We've got x squared minus 6x. Our goal is to turn that into a perfect square, so it'll be x plus or minus some number squared. The trick to do that is to take this number that's now in front of the x and divide it by 2. So we're going to get x, what we want to get then is x minus 3 squared. To do that, we need to add a number to the binomial there so that we get that perfect square. So we'll have 2 times x squared minus 6x. Half of that negative 6x is negative 3. If we square a negative 3, we get 9. So we're going to add 9 there, plus 7. Now to keep the function equal, we have to subtract what we added. So what we added was 9 times that 2 that's out front. So now we're going to subtract the same thing. 2 times 9 are 18. So this, subtracting 18, balances that adding the 9 earlier on. So now we have 2 times x minus 3 squared minus 11. So now you can see this function now is in standard form, so we could very easily write a mapping rule. We could talk about the vertical stretch of 2 and our horizontal translations and so forth, and our mapping rule would be xy maps onto x plus 3 and 2y minus 11. And it would be very quick to write a new table of values and sketch that graph. Now let's do the same process. We're going to do the exact same process that we just did using the general form of the equation, because that's going to give us some really valuable information. So I'm going to factor out that a, that whatever the coefficient of the x squared term is, from the first two terms. So then we'll have x squared in the brackets minus b over ax, because we're just dividing that a out, plus c. Now to get that, complete that square, to turn that binomial into a perfect square trinomial, we are going to cut that number in half. So negative b over a, half of that will be negative b over 2a, and then we'll square that and add that. So we'll have x squared minus b over a times x plus b over 2a all squared plus c, and then we have to subtract what we added up there. So we're subtracting, sorry, and I'm going to have to just put that below, a times b over 2a squared. So a little bit of simplifying to do here. We have a times x minus b over 2a squared plus c. And if I square this first, I'll have b squared over 4a squared. And I'm multiplying it by a though, so I'll have c minus b squared over 4a. If you compare that to what we looked at earlier of f at x equals a times x minus h squared plus k, you can see that The h value will becomes that negative b over 2a, and the k value becomes c minus b squared over 4a. So we can say that our x-coordinate of the vertex is going to be negative b over 2a. Okay, remember the sign needs to change for the h, so the h would be negative b over 2a, which we've got right there. So that also gives us the axis of symmetry. So we know that x equals negative b over 2a will be the equation of the axis of symmetry, and the y-coordinate of the vertex will be given by f at that value. So we can substitute that value into the original function to get the y-coordinate. So now we've got the x-coordinate, the axis of symmetry, the y-coordinate of the vertex, and because the vertex gives us the minimum or maximum value of the function, that's key to solving very many problems. So let's take a look at an example where we can answer some questions about a quadratic function. So I've got f at x equals negative 5x squared plus 10x plus 7. The first question is, does this function have a minimum or a maximum? And again, we just look at the a value. What's the coefficient of x squared? Since a is negative 5, it's less than 0. So that means this is a parabola that opens downward. So the vertex is at the top, so it has a maximum value. So now let's find the maximum value and where it occurs. And remember, maximum value is where the vertex is, and since we know that we can find the vertex easily using that x equals negative b over 2a, we can find the value of our vertex very quickly. So x equals negative b over 2a. So let's look at the original equation. There's my b, and the a is negative 5, so it'll be negative 10 over 2 times negative 5. So we have we have negative 10 over negative 10, which will give us x equals 1. So there's the x-coordinate of the vertex. We can substitute that into the original equation now and say that f at 1 equals negative 5 times 1 squared plus 10 times 1 plus 7. Sorry, ran out of space there. So f at 1 equals 12. Okay, so the maximum value, so the maximum value is 12. Remember, the value is always given by the y-coordinate, so the max value is 12, and it occurs at x equals 1. And then let's think about the domain and range of the function. Since it's a quadratic and there are no limitations to the domain have been stated, our domain will be negative infinity to infinity, and our range, because this is a quadratic that opens downward, it'll have a maximum value, so our range will be negative infinity to 12, whatever that maximum value is. And that's that for that lesson.